inverse trig functions. So inverse trig functions. So let's recall if we have y equals sine x your basic sine wave looks like that, where x is an angle that you input. This is the ratio that you have for that particular sine. For example, sine of 30 degrees is 1/2. Sine of 60 degrees is √3/2. So we input an x, we output a y, so our input is our angle, our output is our ratio. Now, typically, though, especially when we deal with graphs, we use angles in radian measure instead of degree measure. So normally, instead of calling that 30 degrees, we would call that pi/6. Instead of calling that 60 degrees, we would call that pi/3. Then you may recall that when we do inversions, we basically swap the x and the y. So instead of having y equals sine x, the inverse of that function comes from swapping x and y, and then solving for y. So there's not really an algebraic technique to solve that. So in walks the inverse function, and in trig we used this notation to denote the inverse of sine, where that doesn't mean move that to the denominator and it's 1/sine. That just refers to that it's the inverse. Keep in mind that what we're taking sine of, that's our angle. This is a ratio, the result, not ration, the result of taking sine. So when we flip those, this is our ratio, this is our angle. Now, this book normally, instead of using the sine to the -1 notation, it calls that arc sine. Nonetheless, that's a ratio, that's an angle. Now, if we think about the sine wave goes on forever and ever. That's the first period of it, but it goes on, and it goes on forever in both directions. So if we were to flip x and y, then our sine wave, instead of going down the x-axis, it would go down the y-axis. And is this a function? No, that's not a function. So you may recall that inverse sine, that the only ratios we get for sine are -1:1. So the domain is -1:1. Our output is the angle. So the way we restrict this to being a function is we say we're not going to let our range go from positive infinity to negative infinity, even though that sine wave would go on up the y-axis and go on down it. We restrict the range from negative pi halves to positive pi halves. That section of the graph, if we look at just that piece of it, that is a function. So we say that the range for sine negative pi halves to positive pi halves. For cosine, still x is our ratio, and for cosine our ratios can only be from -1 to 1. The same thing happens when we take a cosine wave that goes on forever and ever. So if we rotate that, it goes on forever and ever, up and down the y-axis. So the way we make that a function is we restrict our range from 0 to pi. If you think about it, sine is 1 at 90 degrees, sine is -1 at -90. Cosine is 1 at 0 degrees, cosine is -1 at pi, or 180. For tangent, turns out let's see, tangent is sine over cosine. So when cosine, or when x is 0, we have 0 over 1. When we're at 90 degrees, though, we're at 1 over 0. When we're at -90, -90, this is -1, this is 0, so we're undefined. So we have an asymptote on both sides, and it turns out that tangent does that. So the domain for tangent, not for arctangent, but the domain for regular tangent is -infinity to positive infinity. I'm sorry, that's not the domain, that's the range. The range of regular tangent is -infinity to positive infinity. So when we do arctangent, that becomes our domain. If we were to lay this on its side, we would get that. That goes from -infinity to positive infinity. Our range goes from -pi halves to pi halves. And each of the cofunctions have similar domains and ranges. They're a little bit different, but similar. And let me see, they may list all of those. Yeah, on page 366, they list the domain and range for the rest of the cofunctions. So I'm not going to go into a lot of detail. We'll look at one of those. And let's think about what they are. Cosecant is the reciprocal of sine. So if sine does this, keep in mind not quite. You would think they would, since those are just reciprocals, but once we swap them and then swap x and y, it's going to be a little different. So let's change these to dotted lines. That what you said would seems like that would make sense. But our ratio for sine, the largest it could be is 1, the smallest it could be is -1. Every other number down through here is going to be less than 1 or greater than -1. So let's look right here. Here, sine is 1, so cosecant is the reciprocal of that. So what's cosecant? If sine is 1, then cosecant is the reciprocal. What's the reciprocal of 1? 1. Let's look here. Here, sine is -1, so what's the reciprocal of -1? -1. Well, let's look here. What is sine here? 0. What's the reciprocal of 0? Right. If that's 0, the reciprocal of that is undefined. If cosecant is 1 over sine, when sine is 0, that's undefined. So we have a vertical asymptote there. Every time sine is 0, we have a vertical asymptote. Let's look at this section. Here, sine is getting smaller and smaller. Let's say right here, sine is 1/2. So when sine is 1/2, what is cosecant? 2. If sine were 1/4, what would cosecant be? 4. So the smaller sine gets, the larger cosecant gets. Here, sine is getting smaller, so cosecant is getting bigger. Same thing down here, except they're negative. Sine is getting smaller, so cosecant is getting bigger in the negative direction. Same thing here. So this is cosecant. So for just your basic cosecant, your domain, well, the only numbers you can't use for your domain are 0, anything that makes sine 0, which is 0, pi, 2 pi, 3 pi, 4 pi, and so forth. Your range, well, you don't have anything in here for your range. So your range goes from 1 to infinity and -infinity to -1. Which is kind of weird. So that's your range for cosecant. So arc cosecant, we would take that and we would flip it along the y-axis. Just a second. So if we were to do that, we would have, oh, those would flip too. So we'd have something similar to that. So if that's y equals arc cosecant x. So the domain, which is our ratios, that's going to go from negative infinity to negative 1, and then from 1 to positive infinity. Well, to restrict that so that we get a function, then we're going to have to get rid of a lot of this. So it's basically going to be from negative pi halves to pi halves. Maybe I'm saying that wrong, and I may have had this shifted over actually. No, that's right. Negative pi halves to pi halves. But we can't have 0. Because at 0, we're undefined. Now, I'm not going to make you derive all of that, memorize all of that, but I did want you to be aware of, well, when we pull that up and see that list, let me pull up the book. Why are the domains like they are? Why are the ranges like they are? So there are domain and ranges for our arc function, or also known as our inverters. Now they list our domain a little bit different for arc cosecant. This is just a fancy way of saying that the domain is going to be greater than positive 1 or less than negative 1. So they give us a few problems and they say, well, let's evaluate some of our inverse trig functions. For example, let's evaluate arc sine of root 2 over 2. So if they want the exact value there, think back to the unit circle. Remember that our special ratios on the unit circle are 1/2 root 2 over 2, root 3 over 2. And as far as ordered pairs on the unit circle, which one is cosine and which one is sine? Cosine is x, sine is y. So if we look at our 3 special angles, 30, 45, and 60, this has a y of 1/2 because that's the smallest. This has a y of root 3 over 2 because that's the largest. That has a y of root 2 over 2. So we have a y of root 2 over 2 for what angle? 45 degrees. What is that in terms of radians? pi over 4. Now, all of y'all except Evan had me for 113, and I didn't spend a lot of time worrying about radians in 113 because I wanted us to get used to just, well, what are our general concepts. But in calculus, you're going to use your angles and radians a lot more than you're going to use degrees probably. So remember that that's 30 degrees. And the shortcut I told y'all is that if we have something that is a multiple of that, well, if you want to think about what in terms of degrees, if pi over 6 is 30 degrees, that's just 5 30s, which is what? 150. So instead of having to manually calculate that every time, just remember pi over 6 is 30. Well, that's 5 of those, so that's 150. Pi over 4 is 45. So if we have 3 of those, 3 45s is 135. So I'm not going to go over a lot of these. They're going to give you several problems where they just ask you to do something like this. Just to remember, have you recall how the inverse functions work. They give you a ratio. You find the angle in the appropriate range that has that particular ratio. But what I do want us to spend a little bit of time working with is simplifying some expressions like this. Now, if we had angles or ratios in here, for example, if I had tangent of arc cosine root 3 over 2, then we could just work this inside out and say, well, what angle has an arc cosine of root 3 over 2? If we go to our unit circle, cosine is the x, so which of these has an x value of root 3 over 2? 30. That's the largest value, so the largest x on those would be 30. So that's 30 degrees, or pi over 6. Then we could continue that. Tangent of 30, you could either think about that as sine over cosine, or you could think about it as your triangle and what's opposite over adjacent. If you do it this way, sine of 30 over cosine of 30, that's just 1 over root 3. Or you could rationalize that, root 3 over 3, but that's what we would do if we knew what our ratio was. But here, we're given an expression in place of our ratio, and we want to simplify this expression and come up with some kind of algebraic description of what our solutions are. So let's look at this inside piece. Arc tangent 4x. Now, is this 4x, is that an angle or is that a ratio? That's a ratio. So our answer is going to be what? A ratio or an angle? An angle. So let's just call our answer theta. So let's flip this around. Instead of saying arc tangent is theta, let's say tangent of our angle is 4x. Those statements are equivalent. Inverse tangent of your ratio equals your angle, or this is the ratio for tangent of that angle. Now still, we don't know what x is, so we can't come up with a specific angle, but doing this allows us to come up with a relationship. We originally defined tangent in terms of a right triangle. If we call this theta, by definition, tangent is opposite over adjacent. How do I write this as a fraction? Four x over 1. So if I call this angle theta, opposite of theta, I could call 4x. Adjacent to theta, I could call 1. And I could find the third side of this triangle. Pythagorean theorem, side squared plus the other side squared equals our hypotenuse squared. So 16x squared plus 1 is our hypotenuse squared. So what would our hypotenuse be? How do we get rid of the square? Square root. Now keep in mind, we're wanting secant of that angle. So this inside piece just sets up a relationship. This just gives us a relationship of the three sides of a triangle. We want secant of that same triangle. Let's see, secant is the reciprocal of what? Cosine. Cosine is adjacent over hypotenuse. So this would be hypotenuse over adjacent. Is that right? Cosine, adjacent over hypotenuse, so this is the reciprocal. So the hypotenuse of this triangle is this. The adjacent side to theta is 1. So when we take that statement and dissect it in terms of theta, we get x, an expression in terms of x to be 16x squared plus 1 square root. So instead of, if we wanted to evaluate our expression for several different x values, instead of having to multiply them times 4, take the arctangent, then take secant of whatever that angle is, all we really have to do is substitute that value of x into our expression. So this is just an algebraic way of evaluating that expression. So just kind of a quick review. We draw a triangle that sets up that relationship. Once we get a triangle that establishes that relationship, we apply that to our outside function. Our outside function is secant, so we want secant of that relationship. All right, let's do another one of those. So let's do cosine arc sine x. And we want to come up with an algebraic expression. So let's just call that theta. Or we could rearrange that. That's the angle whose sine is x. So eventually we're wanting cosine of whatever that angle is. So if we draw a triangle, label this to be theta, sine is opposite over hypotenuse. So opposite hypotenuse. We need to find this adjacent side in terms of x. So the adjacent side squared plus x squared equals 1 squared. Side squared plus side squared is hypotenuse squared. So adjacent squared is 1 minus x squared. Subtract this from both sides. So the adjacent side, take square root of both sides. Adjacent side is the square root of 1 minus x squared. So that triangle is an expression of our angle in terms of x based on our ratio. So if we want cosine under these restrictions, cosine under these restrictions, remember that's adjacent over hypotenuse. So adjacent divided by hypotenuse. So the picture is the whole key to the problem. If you don't draw the picture, you have to keep a lot of things straight in your head. But if you draw the picture, label opposite, adjacent, hypotenuse, whichever ones are given, you can find the missing pieces and then express this ratio in terms of those sides. All right, now that's just a little bit of review of trig. That's a review of some of the properties of inverse trig functions. Now what we want to do is take the derivative of these. We've taken the derivative of sine, cosine, tangent, secant, cosecant, cotangent. Now let's take the derivative of the inverse functions. And let's go ahead and do them in terms of u. The derivative of arc sine u is u prime over the square root of 1 minus u squared of arc cosine is almost the same thing except it has a minus in front of it. The derivative of arc tangent, u prime over 1 plus u squared. The derivative of arc cotangent is the same except it has a negative in it. And for secant and cosecant, they're going to be the same except for a negative. So u prime, absolute value of u, square root u squared minus 1. Arc cosecant is the same except for the negative. So when it comes to taking the derivatives, we have all of our other rules. If we have a product, we have to use the product rule. If we have a quotient, we have to use the quotient rule. But when it comes to taking the derivative of an arc sine or an arc tangent or an arc cosecant, we just have to apply one of these formulas to take that derivative. So if we have y equals arc sine 3x, and we want to take the derivative, then we're going to let whatever we're taking arc sine of be u. We need to know u prime and u for our derivative. So if u is 3x, what's u prime? 3. So our formula says to take this derivative, it's u prime over the square root of 1 minus u squared. Or you could call that 3 over the square root of 1 minus 9x squared. Which is kind of odd. Our function is trigonometric. Our derivative is algebraic. There are no trig expressions in this equation. Which the same is true for natural log. That function is logarithmic, while its derivative is just algebraic. Alright, let's do y equal arc tangent of x squared we want the derivative. What is our u? So u prime. And our formula for taking that derivative is u prime over 1 plus u squared. So u prime over 1 plus x squared squared. So 2x over 1 plus, what's x squared squared? X to the 4th. So that's the derivative of arc tangent x squared. What's that derivative? Give you 1 second. 0. Why is it 0? And this one is all of this. Sure. You can do that, or you could. Is there a variable in this? There's no variable in that. So basically, that's just a messy constant. The derivative of any constant, 0. Now, having said that, we do have to be careful. What's the derivative of that? Now keep in mind that the derivative of arc sine is u prime over that. But what's that derivative? It's undefined. Two ways of looking at it. You could say, well, u is 2, so u prime is 0, so that's 0 over the square root of 1 minus 2 squared. Isn't that undefined? Yeah. Another way, this number is not in the domain of sine. Remember, this is our ratio. What are the only values we can get for sine? -1 to 1. So if your function is undefined, then the derivative is undefined too. So a lot of the stuff in this section, 5.6, is simply going to be applying the derivative to some of our, applying our new rules to some of these functions. How do I take the derivative? Now they got an interesting one here. Let's look at taking this derivative. Except I'm going to change it up a little. What's one rule that we have to apply to take this derivative? That's a composite, so we have to use the chain rule. So when we take the derivative, it's the derivative of the outside. This is our outside function. That's our inside function. So what's the derivative of the outside? Minus sign times what's on the inside times the derivative of the inside. But the inside is arc sine x. The derivative of arc sine, that's u prime over the square root of 1 minus u squared. So what is our u here? X. So the derivative of x over the square root of 1 minus x squared. Now notice, how are these two functions related? They're inverses of each other. When we take the composition of inverse functions, what happens? They cancel each other out. So when those cancel, we're just left with that. So we have our minus. When we do that composition, the composition of inverses, think back to 112, the composition of inverses is that. Or we could call that negative x over the square root. All right, now they're going to give some problems in there where they ask you to find equations of tangent lines, find extrema, so forth. All of that is going to be basically applying some of your rules of derivatives. We have our new derivative formulas, and then maybe solving a little equation or something. So the rest of the stuff in this section is really nothing new. What is harder is going to be doing the integrations. So we'll save most of the rest of the time for doing integrations. Let's take a 5-minute break, and then we'll come back and look at 5.7.